Hello physicists and welcome. In this session we'll be covering Kinematics Section 4, Analyzing Graphs. Our learning objective is, I can use a velocity versus time graph to find the acceleration from slope and displacement from area. Let's get started. A graph shows the relationship between two variables, with the independent variable on the horizontal axis and the dependent variable on the vertical axis. The amount that the dependent variable changes as the independent variable is adjusted can be calculated by the slope of the graph or the best fit line. The slope is used to determine related values such as miles per gallon for a car, dollars per pound for produce, or pages per minute for a printer. The slope of a position versus time graph has a special name relating the rate that the position changes with respect to time. It's called velocity. Both the position and velocity describe the motion of an object. Let's take a look at an example. Here we have a turtle moving along at a slow, constant velocity. We'll graph both the position versus time and velocity versus time. We see our position versus time shows a forward motion, and our velocity graph shows a constant velocity. Our velocity tells us the rate of change of position, but it doesn't tell us the absolute position. If I was in a car that was moving north from San Francisco at 50 miles an hour, or a car moving north from San Diego at 50 miles an hour, the speedometer would read exactly the same, but the position versus time graph would be very different. Let's take a look at another situation. We have a rabbit speeding by at a constant velocity. We have a steeper position versus time graph because we have a higher velocity. A greater slope for position versus time means a greater value for velocity. Let's take a look at another example. We have our bike rider going backwards, so we have a decreasing position with time. So the decreasing position with time is shown by a negative slope. A negative slope tells us the rate of change of position. We have a constant negative velocity. Let's go ahead and summarize those. If I have a straight line with a positive slope, I have a constant positive velocity. If, let's see, a straight horizontal line with no slope, I have a zero velocity. Or a straight line with a negative slope, I have a negative constant velocity. Let's take a look at an example. I can replace the movement indicated by the bug and its droppings with a motion map. So I have spots left by the bug every 2 seconds. Let's go ahead and we'll put a number line from 0 to 50 meters. Let's go ahead and give that a direction to the right will be positive. Hey, our first drop was at 0 seconds, and at 2, 4, 6, and 8 seconds. Let's go ahead and give arrows to indicate the direction, and each time it was moving at a constant velocity to the right. The table shows the calculated values for time, position, change of position, velocity, change of velocity, and acceleration. We'll put these into graphs. First, let's start off with our position versus time graph with time along the horizontal axis in seconds. We'll put that at 1 second intervals. We'll have our position along the vertical axis, and we'll put that at 5 meter increments. We'll go ahead and plot our points at 0, 2, 4, 6, and 8 seconds. And we'll go ahead and add a best fit line through there. So our data for position versus time is represented by the graph on the left. Let's go ahead and put our velocity versus time from the graph data, or from the table data shown. We'll put our time on the independent as our independent variable along the horizontal axis, again in 1 second increments. We'll graph velocity in meters per second along the vertical axis, and we'll put that in 1 second increments. Let's go ahead, and we see that our first position is at 5 meters per second, at 2 seconds, at 4, 6, and 8 seconds. We're traveling at 5 meters per second. Let's go ahead and put a best fit line through it there. Good. So we've drawn our position versus time and velocity versus time from our table of data. So now, rather than using our calculated values, we're going to use our position versus time graph to produce our velocity versus time graph. We know that the slope of a line tells us the rate at which the dependent variable is changing with respect to the independent variable. For position versus time, that rate of change is known as velocity. So let's take position at 2 seconds, we're at 18 meters. At 4 seconds, we're at 28 meters. We'll look at rise over run there. So I went from 18 to 28, a difference of 10 meters. My run is from 2 to 4 meters, a difference of 2 seconds. Let's go ahead and calculate what that slope is. 10 meters divided by 2 seconds is equal to 5 meters per second. Make sure we use the units as well. Let's go ahead and put that on the graph. That's our slope from 2 to 4 seconds. Let's go ahead and mark that at 4 seconds. Let's pick two other positions along our line. So we'll look at 6 seconds and 38 meters, and 8 seconds and 48 meters. We'll do our rise over run again. Our rise is 10 meters. Our run again is 2 seconds. So 10 meters divided by 2 seconds is 5 meters per second, and that's the slope between 6 and 8 meters. Let's go ahead and mark it on the chart at 8 seconds. Let's go and put a best fit line through that. And so we've produced the same looking velocity versus time graph by interpreting the position versus time graph as we did when we were looking at the table of data. Hey, if I can produce a velocity versus time graph from a position versus time graph, I can probably produce a position versus time graph from a velocity versus time graph. Let's take a look. Hey, so let's take a look at our displacement for 2 seconds. If we're given a velocity and a time, the area here between 0 and 2 seconds will represent how far we've traveled. So let's go ahead and multiply those out. Hey, so I have 5 meters per second times 2 seconds tells me that I've moved 10 meters, which is my displacement. Let's go and put that position over on our velocity versus time graph. Now, fortunately, we have a starting position of 8 meters. Our final position at 2 seconds will be our initial position plus our displacement. So 8 meters, our initial position, plus 10 meters, our displacement, tells us that we're at a position of 18 meters at 2 seconds. Okay, so let's take a look at how far we've gone from 2 to 8 seconds. It'll be represented by the area of that rectangle. So again, we have 5 meters per second times the amount of time from 2 to 8 seconds. That's 6 seconds. So during that time, we moved 30 meters, which is the area of that rectangle from 2 to 8 meters from 0 to 5 meters per second. Our position at 8 seconds will be our position at 2 seconds plus the change in position known as our displacement from 2 to 8 seconds. We started off at 18 meters and we went another 30 meters, so our position at 8 seconds is 48 meters. Let's go ahead and plot that. Hey, now let's go ahead and fit a best fit line through that. And there we go. Okay, so we've produced a position versus time graph from a velocity versus time graph, knowing the velocity. And the one other piece of information we needed was the initial position. Hey, well, this works out fine if we're going forward. What if we're going backward? Okay, so take a look on the right side. We have an object that's traveling at a minus 4 meters per second. That's a constant velocity. Okay, so, oh, there it is. Our snail's going backward at a minus 4 meters per second. So we'll take a look at what the displacement is over 8 seconds. That'll be represented by that area between minus 4 meters per second and the I guess I'll call it the horizontal axis. So the area of that is going to be minus 4 meters per second times the 8 seconds. So our displacement is minus 32 meters, the minus indicating that we're moving to the left or in a negative direction. Okay, so take a look what our position is at 8 seconds. We need to know our initial position. We'll get that from the graph, plus our displacement. Our initial position is 48 meters, so I take 48 meters plus a minus 32 meters. gives our position at 8 seconds as being 13 meters. Let's go ahead and put it on our chart. And we know that this is constant velocity, so we'll have a straight line on our position versus time graph. And there we have it. What if I have a situation when I'm not traveling at a constant velocity? In fact, our velocity will be changing, and that's accelerated motion. Okay, so our turtle here will start off slow, going a little faster, going faster, going faster. Come on, speed up even more. There we go. Okay. Yeah, so definitely not traveling at the same velocity. If we took a look at our position versus time and our velocity versus time, let's concentrate on velocity versus time. Our velocity started off slow and then got faster and faster. Let's take a look at the position. Our position, remember, the slope of the position versus time graph is given by the amount of the velocity. So when we first started, we had a very slight velocity, so we have a very slight positive slope. Toward the end, we had a much greater value for velocity, so we have a much greater slope. So we have a curved line on our position versus time, and it shows that our turtle was moving a greater distance each second as it went along. Okay. Now again, like before, if we started at a different initial position, either forward or backward, the velocity curve would stay the same. If I speed up going from San Diego to Los Angeles, or from San Francisco up to Santa Rosa, my speedometer looks the same, but my positions are very different. Hey, what if I speed up even more quickly? Our rabbit really will take off, keep going faster. There we go. Okay. Anyway, I see that my velocity starts off close to zero, but by the end of time, it's much greater. Let's take a look at our position versus time graph on the left. We start off with a slope that's almost horizontal and becomes much steeper at the end of our time interval. Hey, let's take a look at the situation where here we go, come on, there we go, going faster and faster in a negative direction. And I start off slowly, close to a zero velocity, and then I have a greater speed, but in the negative direction shown here. Here I'd have a very slight negative slope, a very slight negative slope on the position versus time graph. Over here I have a much greater negative slope, a much greater negative slope on the position versus time graph. Greater negative velocity, greater negative slope. Okay, so let's put some of these together. So if I have an upward curved slope, that tells me my velocity is getting greater and greater. If I have a straight line anywhere on the position versus time graph, if it's horizontal, I have zero velocity. If it's sloped up but straight, I have a constant positive velocity. If it's sloped downward, I have a constant negative velocity, but my acceleration is zero in all those cases. Our acceleration is the rate of change of the velocity. Let's go take a look at one more. What if I have a downward curved slope? If I have a downward curved slope, I have decreasing velocity. If I have decreasing velocity, I have negative acceleration. Let's give some numbers to these calculations. All right. Hey, so I've collected data at 2, 4, 6, and 8 seconds for an object that's speeding up. I'm going to go ahead and put it on my position versus time graph. Okay. And we'll go ahead and draw a best fit line through that. You'll notice it's not straight. It makes that special shape known as a parabola in math. We'll go ahead and calculate, or we'll get from the table our velocity values. So we plotted them at 2, 4, 6, and 8 seconds. So we'll go ahead and put our best fit line there, which happens to be a straight line. The rate of change of position with respect to time is known as velocity and is shown by the slope of the position versus time graph. The rate of change of velocity versus time is shown by the slope of a velocity versus time graph and is called acceleration. Let's take a look at this. We can see that our velocity is changing as a function of time. Let's figure out what the slope of that is. We'll pick out a couple of points on here where they cross grid lines. Let's take a look at the rise over the run. The rise is 3 meters. The run from 1 to 7 seconds is 6 seconds. So the slope of this is the rise divided by the run. The rise of this is 3 meters per second. We'll divide that by 6 seconds. We get a value of 0.5 meters per second per second. Now, before we use the area of a velocity versus time graph to give us displacement, and we can do it in this case as well. And so I have my velocity versus time graph, and I want to see how far I've moved in 4 seconds. So I'll do that by looking at the area from 0 to 4 seconds. This time, instead of a rectangle, it'll be a triangle. The area of a triangle is 1/2 height times base. So it's 1/2. Our height is 2 meters per second times the base, 4 seconds. We know our displacement is equal to 4 meters. Let's come over to the position versus time graph. Okay, so our position at 4 seconds is going to be our initial position, 2 meters, plus our displacement, 4 meters. Tells us our position at 4 seconds. So yes, our position at 4 seconds is 6 meters. Let's take a look at the displacement from 0 to 8 seconds. Would be represented by the area of this larger triangle. Again, it's 1/2 base times height, so 1/2 times 4 meters per second times 8 seconds tells us our displacement is 16 meters. So our position at 8 seconds is our initial position plus the displacement over the 8 seconds. Our initial position is 2 meters plus our 16 meters of displacement. Our position at 8 seconds is 18 meters. Let's go ahead and plot that. And we'll bring in a best fit line. Nice parabolic curve. Let's see if this technique works for decreasing velocity as well. And so I have a velocity that's starting off at 3 meters per second, and then 10 seconds later I'm traveling at 1 meter per second. Okay, the slope of this line is starting at 3 and ending at 1. Let's go ahead, and our change in velocity is minus 2 meters per second divided by 10 seconds, so our acceleration is minus 0.2 meters per second per second. Again, to figure out the displacement, we'll have to take a look at the area for the velocity versus time graph, which will be composed of a triangle plus that rectangle. So we're going to have to take a look at the area of a trapezoid. And the area of a trapezoid is 1/2 height 1 plus height 2. So we're averaging the two heights times the base. Okay, so that's equal to 1/2 the height on one side, 3 meters per second, plus 1 meter per second, times our 10 seconds. Our displacement indicated by this area is 20 meters. So our position at 10 seconds is going to be our initial position plus the displacement. Our initial position in this case was 15 meters plus our displacement of 20 meters tells us our position at 10 meters is at 10 seconds is 35 meters. Let's go ahead and put that on the graph. A quick calculation of the displacement at 5 seconds would tell us that the position is 27.5 meters. Leave that for an exercise for you. Let's go ahead and put a best fit line in there. And then we have a nice curving line there. Notice it's a little flatter at the 10-second end and a little steeper at the 0-second end. So let's go ahead and wrap this up. So now, can you use a velocity versus time graph to define the acceleration from slope and a displacement from area? So for now, that's physics.